Formal charges are very important. They're as important as the octet rule. These are your best friends, the formal charge and the octet rule. So formal charges arise quickly from the idea that we can draw two structures, even if we use the rule for the honk 1, 2, 3, 4, but some may be charged molecules, and get two structures that satisfy the octet rule. The question is, which one do we choose? So that's what we use. We use the formal charge to help us out. Now, in this class, while in Gen Chem you did say, okay, let's use this one structure, compare which one is better based on the formal charges. In this class, we're more concerned about finding the formal charge on the structure rather than just calculating it every time and determining which structure is better. So that's what we're going to do in this case. So in this case, look at CO2, carbon dioxide. It has two structures. Which one is the correct one? Well, the rule is you have a formula that you can use to calculate which one is better. And the formula is down here. It's called the formal charge. And it's the number of valence electrons minus the number of non-bonding electrons. Those are basically, ask yourself how many electrons are in the lone pairs. Lone pair electrons, and of course the number of bonds. So for this class, you need to be able to determine how to calculate the formal charge using this formula, or there are two other ways that I'm going to show you in addition to that. So this is going to take a little bit longer, but it's the surefire way of calculating the formal charge. So again, this is a review from Gen Chem. Here's what you do. So for the first one, we say we have two oxygens that have the same bonding. And the carbon here has a 4 bonds. Now, if you use this formula, you're going to write FCO. And the reason why I'm only going to do one oxygen because the bonding is the same. Notice that this oxygen has 2 lone pairs and 2 bonds. It's a double bond. And this one has 2 lone pairs and also 2 bonds. So you can do both, but that would be redundant. Okay, so we're going to start by asking ourselves, how many electrons or valence electrons does oxygen have? So if you have a periodic table, look that up. Well, it's 6. 6 valence electrons. Minus. Then you ask yourself, on, let's say, only one oxygen, okay, how many electrons are in the lone pairs? Well, we have 1, 2, 3, 4. And then how many bonds does it have? 2. Okay, so that would be 4 plus 2 is 6. So 6 minus 6 is 0. So that's a 0 formal charge, and you put that above it. And now this applies to the other one. Now do the carbon. And in this case, a carbon would be 4 valence electrons. Look it up from the periodic table. And minus any electrons in the lone pairs. There are none. No electrons in the lone pairs, because there are no lone pairs. Plus, how many bonds does it have? Well, it's 1, 2, 3, 4. So what's 4 minus 4? That would be a 0. So it also has a 0 formal charge. The formal charge simply tells you, gives you an idea that an atom has, whether it has too little or too much or the right amount of electrons, or better technical term, electron density. No atom wants to have too much. So this looks perfect. This is going to be the structure, but because again, 0 means it has the right amount. When you do the second one, now this oxygen is different from that oxygen, so we have to separate them. So we're going to call this one on the right oxygen A, and this one we're going to call it oxygen B. And let's start with oxygen A. O, and we're going to say A. Okay, how many valence does oxygen have? 6 minus How many electrons in the lone pairs? 6 plus how many bonds? 1. So that would be 6 minus 7, which is -1. So there you go. You now have a -1 charge on that oxygen. Now, the carbon is next. You can obviously look from here. That was when it was 4 bonds, it's going to be 0, but we're going to show you 4 valence for carbon minus count any electrons in the lone pairs. There are no lone pairs. Plus 1, 2, 3, 4 bonds. So that would be also a 0. And then finally, for oxygen B. So oxygen B, again, start with the number of valence, 6 minus how many electrons in the lone pairs? You have 1, 2. Plus how many bonds do you have? 1, 2, 3. So that would be 5. 6 minus 5 is +1. Okay, they still all add up to 0. But this tells us that this oxygen has too much electron density, and this one tells us it has less, and they need to be at the right amount. So anytime you have formal charges close to 0, or they are 0, that would be your correct structure. So again, this would be the correct structure because the formal charges are 0. Okay, 0 formal charges. Now, having said that, let's look at some other ways of doing this. Yes, you can have a quick shortcut, and I'm going to show you. Now, the second one is giving you another method, is you can really memorize this table. And this is going to tell you the formal charges. But let's actually look at an idea like what is so special about this table. So again, you will see when we get to the chapters ahead that the whole thing about organic chemistry is about electron-rich atoms are attracted to electron-poor atoms. So the plus and the minus indicate whether an atom is electron-rich or whether it's electron-poor. Formal charges as, the case in this case. So that's why it's imperative for us to actually know them and find them. So let me show you the second method. And I don't want to spend too much time speaking here, but I show you. So I'll show you. The other method is the following, is you go back to HONC 1, 2, 3, 4. Okay. In fact, let me just draw that in the middle because I need to write above and beyond, above and below. Now, this is a good method, and I wish I can give you, a very magical method, but there's a part when we come to the oxygen and the carbon where we need to remember a little bit, or remember a few things about the concept here. So let's look at it. How to calculate the formal charge? Well, mainly the formal charges you're concerned with are oxygen, nitrogen, and carbon. Now, for oxygen, let me start with that, and then if we need to talk about the halogens, the hydrogens, we can. For oxygen, anytime you have more bonds, okay, you have more bonds than this number. So in this case, for oxygen, if you have 3 bonds, then it will be here will be positive. Okay, so I'm going to write somewhere here on the side. Okay, so here, positive. Anytime nitrogen is above, it's also going to be a positive. So 4. Now, I'm going to leave the carbon alone. That's why I told you it's not a magic formula, but it will help. When will carbon be positive? Okay, this one will be positive when it has less bonds, but no more electrons.